All right, let's go over the practice test for the Unit 5 learning targets 5 through 9. So it says move each of the following into the correct category. So our category choices are chemical change or sign of a chemical change, and I'm going to call that CC, or a physical change, PC. And let's just talk about what the difference is here. So a chemical change is a rearrangement of atoms, the reactants, to form a new product. Versus a physical change is simply often a phase change. Example, H2O, ice, solid, melting into H2O, liquid. See, the atoms are not rearranged. They're not forming a new product. Versus like up here, maybe we have the decomposition of hydrogen peroxide forming H2O and O2. These are new things. So that's the big difference between a chemical change and a physical change. Physical changes too aren't always a phase change. It could be like something cut, like a blade of grass, I think is one of the examples. So up here, so melting ice, that's a phase change, a physical change. Excuse me, spring allergies. The formation of light would be the sign, a sign of a chemical change. The formation of gas bubbles not due to boiling, that's chemical change. Color change is often due to a chemical change. Same with a new smell. But boiling water would be a physical change. That's just H2O liquid turning into H2O gas. Same here, a substance freezing, that's simply a physical change. Cutting grass, like we said, cutting, that's just a physical change, versus cooking an egg, that's a chemical change. You're forming something new. Okay, match each of the following. I like to look at the definitions first. The numbers out front of the chemical formulas, that would be the coefficients. Those are the numbers out front. And then let me get a different color. The numbers telling you how many of each type of atom there are in a substance. Those are the subscripts. Located to the left of the equation arrow, that's what you start with, the reactants. Located to the right of the equation arrow, that's the products. And let's get one other color. Solid, liquid, gas, aqueous, those are phase label examples. Match each of the following with their correct reaction type. Well, combination is when you've got A plus B making AB. So are there any that look like that? One thing to the right of the arrow, and that would be this one. Na plus Cl2 makes NaCl. A combustion reaction, that's often a bunch of carbons and hydrogens, called a hydrocarbon, plus oxygen, making carbon dioxide and water. That's the general format of many combustion reactions. So that matches that top one. And decomposition is the opposite of a combination. It's when you have something that's breaking into parts. List the 7 diatomic elements. So I like to think of Hofbrinkel: hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, chlorine. Which are the correct products of AlF3? So for decomposition, you need to think breakup and then think about Hofbrinkel. So break everything up and don't pay attention to any subscripts. Just write the elements. And then if anything is in Hofbrinkel, it gets a 2. That's it. So that would be this third one down. Type the products of almost every combustion reaction. CO2 plus H2O. Type the correct product of Na plus N2. So when you're doing combination, you need to think crisscross. And what I mean by crisscross is crisscrossing the charges from the periodic table. So we would crisscross the 3 down here, the 1 here, but we don't really need to write the 1. So the product would be Na3N. For the energy diagram pictured, match each of the following colored areas with a correct description. So the pink area at the top is when everything is single. That's where the atoms are alone. Okay, let's do the blue. The blue area is on the way up. That's the activation energy, the energy required to break the bonds of the reactants. And yellow is energy released as the bonds of the products form. Okay, it says the activation energy for a certain reaction is 100 kilojoules. Okay. The total energy released is 250 kilojoules to get to the products. So what's the difference here? What is this? Oops, I drew that a little too long. What is the difference between the reactants and the products? That's called the heat of reaction. Well, 250 minus 100, this is not drawn to scale, it'd be minus 150. And it's exothermic because it's releasing energy overall. Draw an energy diagram for the reaction. It's endothermic. Okay. A plus B makes AB. So A plus B makes AB. Okay, so we've labeled our reactants and our products. Activation energy. And also write it on here just so it's super clear. Reactants, product. Activation energy. That's how much it takes to get to the top of the mountain, how much energy is required to break the bonds of the reactants. And the heat of reaction is the difference between the reactants and the products. What is the coefficient in front of Al2O3 when you're balancing this equation? Well, let's do some balancing. We've got aluminum and oxygen, 1 aluminum on the left, 2 on the right, 2 oxygen to the left of the arrow, and 3 on the right. Make odd numbers even is a good practice to adopt. 2 times 3, that's 6 oxygens. And then 2 times 2, that's 4 aluminums. Another way of doing it is actually writing out 2 Al2O3s and counting and saying, okay, that's 4 aluminum and that's 6 oxygen. So then we go over to the left side. We've got to put a 4 in front of the aluminum to make it 4 and a 3 in front of the O2. So to answer this question, it's a 2 that goes in front of the Al2O3. What are the coefficients for the following chemical reaction? We've got Ks, Cls, and Os. 1 K on the left, 1 on the right, 1 Cl on the left, 1 on the right, 3 oxygens on the left, 2 on the right. Good rule of thumb is to make odd numbers even, so turn that oxygen into 6 from a 3. That makes the Ks and the Cls 2. So then you need a 2 in front on the right, and you need a 3 times 2 to make that 6. For the combustion of butane, match the molemole ratios for each of the following. So what is the molemole ratio of CO 2, which there's an 8 in front, to H2O. There's a 10 out front. So that would be 8 to 10, which simplified would be the same as 4 to 5. So that would go with this last one here. Next, what is the ratio of O2 to H2O? So that's 13 to 10. It's just what are the numbers out front. So that one goes with this one. And then we've got O2 to CO2. That's 13 to 8. So that's this one here. Then we've got C4H10. There's a 2 out front to the oxygens. So that's 2 to 13. And then we've got a 2 in front of the C4H10 and a 10 in front of the H2O. That's a 1 to 5 ratio. And then we've got C4H10, that's 2. And then what's in front of the CO2? 2 to 8. That's the same as 1 to 4. Okay, what if you want to make exactly 100 grams of water? How much oxygen gas will you need in grams? Okay, you want to make 100 grams of H2O. First thing, we've got to get grams into moles, so we can use the mole to mole ratio. 1 mole of H2O from the periodic table weighs 18.016 grams. How did I get that? I looked up hydrogen, like the square, and at the bottom it's 1.008. And there's 2 of them because it's H2O. And then I looked up oxygen's square, and it's a 16. So plus 16. So that added up to 18.016. Next, I need the numbers that are out front. What's in front of the H2O? What's in front of the O2? Turns out it's a 2 to 1 ratio, meaning for every 2 moles of H2O, you only need 1 mole of O2. Now I need to get moles of O2 into grams. So same thing, O2 would be 2 times the molar mass of 16. 2 times 16 is 32. Now I take everything on the top, 100 times 1 times 1 times 32, divided by 18.016 times 2 to get my final answer. So let's see, what is this? Bottom is 36.032. The top is 3200. So 3200 divided by 36.032. Answer, 88.8 grams of O2. Final answer. Oh, good, that's a choice. Your theoretical yield is 15 grams. You perform an experiment and you get 12.5 grams. What is your percent yield? Well, percent yield is always your actual over your theoretical times by 100. So that would be 12.5 divided by 15 times 100. So when I punch that into my calculator, 12.5 divided by 15 times 100, that's 83.3%. And then we have one more question to do. It says, your friend asks you for stoichiometry help. She says the problem is the following. You've got 25 grams of sodium and you need to know how many grams of chlorine will react with it. She shows her work like this. So let's see, she's got 25 grams of Na. Uh-oh, I already see a problem. She's got 1 mole of Na on the bottom, but that's not going to cancel out her grams. So she should have flipped this around. And then she's got 2 moles Na for every 1 mole Cl2. 1 mole Cl2 weighs that much. And then she probably got way too big of a number because her 22.99 should have been on the bottom. So her mistake was, in her first set of parentheses, she should have 22.99 grams of Na on the bottom and 1 mole Na on the top. And that is it for the practice test.